Welcome to this next video for the reverse engineering course of simplilearn security. This video is associated with chapter number 11 of the reverse engineering course. During this video, we are going to examine in practice all the anti-reversing tricks we talked about during the 11th chapter of the reverse engineering course. So let's try and run the application just to see if we can do a quick identification of any kind of anti-reversing tricks. Let's try to run it again while OLI is active. We see that the application won't start, which means that in some way it detects that OLI debugger is running. But this time we don't see a message box that notifies us about the fact that the debugger has been detected, which makes the whole challenge more realistic and more fun to solve. So let's run the application with OLI debugger this time. And we see that the application just terminated. And let's examine the stack. We see that there is a call to the terminate process API from this address here. So let's follow in disassembler. And we can see this function here that calls the terminate process API. Now if we select the first instruction, we can see that only displays the addresses where there are calls to this function here. So let's go on the first one. Again, you can see a conditional jump that if this is effective, is going to skip the call that terminates the process. And just before that, we see another call here. So let's restart the application and run. So now we stopped at our first breakpoint at this address here. So let's step in and let's examine a little bit this function. You can see again a call to this API here with a flag snap process. So we know now that the application is going to retrieve a list of all running processes. We can see again a call to the process32 first API that is going to retrieve information about the first process in the list. Let's see what else we can find. We can see that this function is quite big. We can see here a call to the process32 next API, which goes through all the running processes in the list from the list. So let's start stepping over and see what we can find. So it successfully retrieved the running processes list. You can see a valid handle in EX. Now it's going to retrieve information about the first process. You can see here index points to the name of the first process from the list. It's going again to use a function here to convert this to ASCII. So we can put a breakpoint here and run, just to avoid stepping over all the loop. Now let's place a breakpoint here just to avoid this loop, since we can't really see anything very interesting. And again. And we arrive now at this call here. let's examine the stack. You see now that it's going to push two parameters, which are two strings, the process name of holy debugger and the name of the first process from the list of the running processes. So it checks again if these two match, and if they don't, it's going to jump. And it's going to call process 32 next in order to go through the next running process from the list. So let's put again a breakpoint here, remove it. Let's continue stepping. And we arrive here at this call. Now it checks the next process name, again with the holy debugger process name. So let's put a breakpoint here, run, and let's see now what happens. Once it has found the process name of holy debugger. Let's see if there is anything interesting here. Just press enter. You don't have to step in, just to see if there is anything interesting here. This is probably code entered by the compiler. So let's see what's going to happen. So we see that here AX is going to be set up to 1. Then it decrements CX. So if it is 1, it's going to become 0. And this is not going to be, this jump is not going to be executed. So it will enter the function that terminates the process. So at this point, we know that it checks for the process name of holy debugger. So let's run again, enter here, and let's go to the process 32 next API. And what we can do is, let's run, we can make this API to always return 0 in EX, so the application will think that has already gone through all the running processes without finding the process name of holy debugger. So now it's going to return 0, but when we decrement this, it becomes -1. So it's not 0 anymore. So this is going to be executed, and we will skip the call that terminates the process. So let's now go and see what happens for the next trick. So let's step in inside that function. Let's start stepping over. We can see here hard-coded the name of the Windows Explorer. We see here that the application is going to retrieve its own process ID and store this to a local variable at EBP-78. Then it's going to go again through it's going to take a snapshot of all the running processes, then retrieve information regarding from the first process from the list. We can just skip these loops here until we see something interesting going on. We see now that it tries to find Windows Explorer process. and it's going also to see if this process matches our process ID. This is actually it's going to see if the process ID of Explorer matches the process ID of our process. Of course it doesn't. And then it's going to call process to next again. But let's unpatch it and do selection, so we can have this whole operation working. Let's put a breakpoint here where it compares these two, the current examine process from the list and the hard-coded name. Let's put a breakpoint here and just run, because we know that once it will find the matching process name, it's going to stop here. Let's run with F9. Now it's going to retrieve in ECX the process ID of Explorer. You can see, if we go File, Attach, you can see that the process ID of Explorer is that one here, and it's going to store that in the local variable at BP-80. And it's going to loop again. We're going to put also a breakpoint here. The execution will arrive here once there will be no processes more to check from the list. And now what it does is that it moves to EX, this value here, which is 3B8. And let's see in which process this match. So 6B0, which is here, is the actually it's going to compare 3B8 with 6B0, which 6B0 is as we know the process ID of of Windows Explorer, and then it's going to check this with this address stored here, 3B8, which it is actually the process ID of Oli debugger. So if I start another process of Oli debugger, it's going to display the process of the other instance of Oli, which is 3B8. So what it does is it checks if the parent process of this application matches the process ID of Explorer, which means that the legitimate parent process should be explorer.exe, but in this case the parent process of the application is Oli debugger because it has been started through Oli. So the application now has detected a reversing tool because the parent process ID of the application doesn't match the process ID of Explorer. So it's going to put 1 to EX. And it's going to call the terminate process, the function that contains the call to the terminate process API. Now we can skip this and just set new origin here, and we can go and see the next trick and see what is going to happen next. So let's step in. We see again that it's going to retrieve a snapshot of all the running processes, and we see also that now for every process, first for the first process from the list, it's going to retrieve a snapshot of all the modules loaded in this process, like all the dynamic link libraries. So you see, for example, now it's going to convert this again to ASCII. Let's skip this loop here. As you can see, it now checks if this module name matches this module name here, which is a default module loaded by only debugger. So we can now detect a reversing tool, in this case only debugger, through one of its loaded modules. So now this is going to loop for other loaded modules. I can set a breakpoint here and run. You can see now it checks the next loaded module. You can see the next one, press F9 again, and the next one. So let's now remove this breakpoint from here and put a breakpoint on the process 32 next API. And in order to skip this trick again, because basically what it's going to do is going to go through all the processes and then check all the modules of each process and see if any of them matches that specific module name that is loaded by all debugger. So what we can do is just trick the application again that it has gone through all the processes without finding what it was looking for. So we'll stop here. Now it's going to return 0. By decrementing this is going to become -1. So this jump is going to be executed, and then we arrive in this next call for the next trick. So let's step in. Let's just press enter to see what is here happening. Let's step in. We can see that it's going to store this value here at this value plus C, so following down memory address, you see. Now it's going to retrieve that value back to EDX and then place it in this local variable here at EBP minus 4. And it's going to call this function again. And it's going to compare index with this value here, and if it's not smaller than this value in this local variable, this jump is not going to be executed and it's going to return 1. And this trick now has been triggered, but we still don't know what is the logic behind this trick. But at least at this point we know how to bypass the rest of them. So what we can do is go a little bit back and try to examine what happened after the previous trick when we arrived here. So I'll put a breakpoint here and load the application again. I know that I need just to patch the process32 next W API in order to bypass the rest of the tricks. Just run. We can remove these breakpoints from here. So we arrived now at the breakpoint we just set in this address here. So as you can see now, it's going to push the value of this local variable on the stack. So let's see if there is any other reference to this local variable here inside this function. Now this function starts here. So let's see if there are any other references to EBP minus 48. We can see a reference here. Let's put a breakpoint here. We can also see another reference here. So I'm going to put a breakpoint on this call instruction here. So we have found some references on the top of this function. We can see some more references here. So let's start again. Let's patch this API here so we don't have to bother with the rest of the tricks. Let's also see, just press enter and see what's in this code here. Okay. So it's going to store in this local variable the value of EDX. Let's follow it down. So then it's going to push the value of EDX again, which is now stored in this local variable here. And then let's enter this call and see what happens. We see that it calls getCount API, and is going to move to ECX, again the address here, this one, and it's going to save the value of px, which was returned by the call to the getCount, into this address here, falling down. So now you see that in this address at D7AC70 is now stored the value of EX, which was returned by getCount. So let's now run, and now it's going to push this value, again this address, in the stack, and it's going to call a function, and we see that it's going to call getCount again. And now it's going to move the next value at this address here plus 4. You can see here ECX plus 4, so the next entry here. Now you see that it saved the new value of EX returned by getCount API here, and this is the previous one at the beginning of the function. So now it pushes again the address of the first entry. Let's enter this function. Let's enter again. We also see that at this address we see EX plus C. So at 7C is going to store this value here, 7D0. Is going to move then this value to EDX, and then move it to the local variable at EBP-4. Then it's going to push as a variable again the first entry, the address, and call this function. Now we have in EX the value of address for the first entry, and then in EDX it moves the second one, and then it's going to subtract from the address contained in this value here, actually from the value here, this value in EDX, which is the second value got from the getCount API, is going to subtract the first. So this is the result here, and it's going to store this value at EX minus 8, so here it's going to go back, it's going to read this value back to EX, here it is, the result from the subtraction, and then it's going to check if this value here is smaller than 7D0, which is not, so this jump is not going to be executed. So what we see is that it calls 2 times getCount API, one versus the beginning of the function and once versus the end, and it subtracts the 2 results. So 7D0 in decimal is 2000, which is actually 2000 milliseconds. So what this function is doing is that it's checking if the time elapsed for the execution of the code from the first call to the getCount and after the second call to the getCount is more than 2 seconds, which means that someone is taking his time executing the code and analyzing it, because otherwise the execution of the code is much faster. So what we can do, a simpler way for this simple implementation of the time checking trick, is that once we patch again the process to next WAPI, we can go to the getCount and make it always return 0. We can either write XOR EX and read, or we can leave it, execute the code here and put just one instruction here, sorry, XCS. So it will always return 0. So let's run. You can see that we call the get count, it returns 0 because you see we modified it. So now it's going always to return 0. So if you see the values here are 0. The first entry from the first call to the get count, the second, and also the result of the subtraction, because the first and the second counts were 0, so it just subtracted 0 from 0 and the result is 0. So this, of course, check is validated because EDX is 0, which is a smaller value than 70, which is the 2000 milliseconds. So also this function is going to return 0, and we're going to jump. And we managed to bypass all the tricks. We can just press F9 to run. And basically this is it. So we saw that just by patching 2 APIs, we managed to bypass 4 different reversing tricks. The first 3 were based on information retrieving from the processes running. So by patching one API, we managed to skip the checks regarding the only debugger process running, the fact also that the parent process of our application is not Windows Explorer, but it's only debugger. And we also managed to bypass the check regarding a specific module loaded by only debugger. And finally, just by patching the getCount API, we managed also to bypass the check regarding the execution time elapsed, actually the time elapsed for the execution of a specific code block between the 2 calls versus the getCount API. So I hope you had fun again. There is one more video regarding the anti-reversing tricks, which is associated with the next chapter. So you can just go back, have some fun playing with those tricks, and see you in the next video.